Okay. Good afternoon, everyone. This is your fourth recitation in solid waste management course. In this recitation, we will have three different questions. And while the first two are related to municipal solid waste processing, the second one is about material separation. Let's start with the first question. In this question, we have a shredder, and we use this equipment to reduce the size of solid materials. And thanks to this method, we can obtain a waste that has uniform particle size. And there are different kinds of shredders, such as horizontal and vertical. And in the figure given in the right-hand side of the slide, you can see a horizontal shredder or hammer mill example. And I want to show this figure to you in order to visualize the question that we'll solve soon. And in this question, the waste flow rate is given as 3.5 tons per hour. And the question says that while the size of 80% of material is smaller than 17 centimeter in the feed side, and also the characteristic size is specified as 2 centimeter. And moreover, N constant and bond work index are given as 1 and 445 kilowatt hour per ton, respectively. And by using the given information, we need to calculate the power requirement for a shredder. Actually, we interested in this type of calculation or let's say information because, you know, hammer mills are grossly inefficient equipment and energy requirements of them increase with the feed rate. And therefore, if we want to operate shredder machine properly, we need to know the energy requirements. However, accurate estimation of this parameter is not possible. Therefore, empirical relationships are used in the power requirements. And in your lecture notes, you found the equation that is shown in this slide by deriving the Rosen-Rambler equation. And we will use this formula to estimate the power requirements of shredder. And remember, the part that is shown inside the red square represents the goal product size. And all parameters are given in the question, but we will be careful about the units. For example, LF value, which represents the size for 80% particles is smaller than in the feed side, is given as 17 centimeter in the question, as I said before. But we should use micrometer. So we have to convert unit from centimeter to micrometer. And the similar situation is valid for characteristic size that represent the size at which 63.2% of particles are smaller. And to provide the unit consistency, we should again use the micrometer for the characteristic size also. And as I said before, for the parameter of EI or work index, we should put the number of 445 into our equations. And for the X0 and N parameters, we should put 20,000 that comes from the 2 centimeter to micrometer conversion and 1 respectively. And finally, for the LF parameter, we should use 170,000. And as a result of this calculation, the power required for 1 ton of material is calculated as 14 kilowatt hour. But our flow rate or feed rate is equal to 3.5 tons per hour. So we should multiply these two numbers together and find the required power amount as 49 kilowatt hour. Well, this is the end of question 1. If you have any questions, you can ask me at this point. If you don't have any questions, let's continue with the second question. This question is again related to the shredder, and the constant and characteristic size are given as 1 and 2 centimeter respectively. And this time we should find the 90% passing size. Here you can see the representative visual of this question. Basically, we try to find the size that 90% of particles can pass through and the remaining 10% of all particles cannot pass. To solve this question, we will use Rosen-Rambler equation again that is shown in this slide. If we arrange this equation by taking natural logarithm of both sides, after we send 1 to the left-hand side of this equation, we can obtain the second equation. Then, in this equation, person passing by weight, or let's say Y value, is given as 90%. And the other parameters, which are n and x0, are also given also as 1 and 2 centimeters. If we put all values into the second equation, we can obtain the size that 90% of particle can pass as 4.6 centimeters. And actually, this is the end of second question. I think that was pretty straightforward, but if you have any questions, you can ask me again. If you don't have any questions, let's continue with the last question of today's recitation. In this question, we will use thermal screen to separate glass from other materials. You can see one of the examples or figures of this equipment. This equipment works with the principle of rolling at low speeds, and there are different tumbling motions such as cataracting, cascading, and centrifuging, as you know from your lecture notes. And efficiency and recovery of this equipment changes with this tumbling motion. And today, in this third recitation question, we are going to calculate the recovery, purity, and efficiency of this equipment based on the following experimental data presented in this question. In this slide, you can see the representative figure for this question. We have an input or flow that is shown in the left-hand side of the thermal screen, while the underside of the thermal screen is called as underflow. The right-hand side of the screen name as overflow. Also, we try to collect glass in the underflow part, and the remaining part is accumulated in the overflow. And moreover, x0, x1, x2 are used to represent glass. y0, y1, and y2 are used for the other components. And to solve the question, we need to know the amount of glass and other components in all parts separately. To do that, let's check the information given in the question. Firstly, the flow of commingled municipal solid waste is given as 100 tons per hour, and the underflow mass per hour is 10 tons. And since the total mass of output has to be equal to input value, the overflow amount is equal to 90 tons per hour. And then, since in the question, in the mass percentage of glass in feet or flow part is specified as 8%, the flow rate of glass in the feet is estimated as 8 tons per hour. And the remaining part, which is 92 tons per hour, comes from the other components. With this way, we have completed the required information in the flow part. And now let's continue with the underflow part. In the question, the mass of glass in this part is given as 7.2 tons per hour. And as we discussed before, overall mass of this part is equal to 10 tons per hour. And therefore, the mass of other components can be calculated as 2.8 tons per hour by subtracting the glass amount, which is 7.2 tons per hour from the 10 tons per hour. And now we have completed the underflow side also, and the only missing part is overflow. And since total amount of glass and other components cannot be changed depending on the mass balance, we can find their amounts by subtracting the amounts in the underflow part from input part. And therefore, while the glass mass is equal to 0.8 tons per hour, other components mass is estimated as 89.2 tons per hour. And now we are ready to calculate recovery, purity, and efficiency of our thermal screen. And the required equations about them have been discussed in your lecture notes. And to calculate recovery rates of glass in the underflow, we need to divide the amount of glass, which is 7.2 tons per hour, found in the underflow, that is desired site for glass, let's say, by the initial amount of glass, which is 8 tons per hour, and times 100%. And therefore, we can obtain the recovery rate as 90%. And that is 90% of glass can be recovered from commingled municipal solid waste with the thermal screen. And then let's have a look at our purity values for overflow and underflow. And remember, the desired materials for the overflow is other components. So we find the purity based on them. And to do that, we should divide the mass of other components found in the overflow, which is 89.2 tons per hour, by the total mass of overflow, which is 90 tons per hour and times 100%. And therefore, we can find the purity of overflow as 99.1%. Then the similar calculations are done for the underflow part. Since this time the desired material is glass, we will find the purity value based on that. And to calculate it, we should divide the amount of glass found in this part, which is equal to 7.2 tons per hour, by total mass flow, which is 10 tons per hour, and again multiply with 100%. And with this way, we can estimate the purity of underflow as 72%. And to summarize what we have done so far, to find recovery, we look at the different compartments, but for the purity part, we examine the compartments one by one. And now, as a final step, we will calculate the efficiency of the system. You know, we can use the efficiency instead of recovery and purity to express the effectiveness of our separation. And to calculate efficiency, two equations called Rietamasa-Worrell-Stessel can be used. And here you can see this equation in the slide. And since we have all the required parameters, we can directly put them into our equations and calculate efficiency values separately. For example, we found X0 value as 0.8 tons per hour, and we should put this number directly into our equations. And actually, this is valid for other required parameters also. After we apply our values into our first equation, we can obtain efficiency value as 87%. And for the second equation, this value is equal to 93%. And remember, we cannot compare these two efficiency values each other for the same separator, of course. Actually, well, this is the end of last question in your fourth station. Any questions about the last question?